Now that we're armed with the ways of thinking about differential equations in state space form and their homogeneous response, let's look at the same second-ordered linear differential equation with constant coefficients and put it into state space form, which effectively in this case, because it's a homogeneous equation, there's no input, that just means specifying the matrix A that relates the derivative with the state x. And then what we'd like you to do in the second part is to go ahead and express the solutions based on the last set of slides and discussion in terms of the eigenvalues and eigenvectors of this matrix A. And so one of the important steps in that process is finding the eigenvalues. So that's going to be important, finding those eigenvalues. You can go ahead and write down the eigenvectors in terms of V1 and V2. You don't have to find those specifically, but you do need to find the eigenvalues with respect to these parameters A0 and A1. So go ahead and start that, and then we'll go through the solution. So to specify state space form, we can pick x1 to be our output y. So, and we can pick our second state, x2, to be y dot. And so this is the most natural choice, but again, there are many different choices you could make. So in that case, x1 dot is simply y dot, which is x2, and x2 dot is y double dot, and so that's when we go up to this differential equation, and so we see that y double dot is just minus a1 y dot, so that's x minus a1 x2, and minus a0 y, which is minus a0 x1. So by this point, getting into the state space form, at least something as simple as this particular example, should be very easy. And if it's not, it's a great opportunity to kind of either look at a couple examples or come and chat with myself or the TAs. So once we have these expressions, we can write essentially, remember, x dot is simply just x1 dot, x2 dot in a vector. And so that is going to be, so remember, x here is then just x1 and x2. So to write x1 dot, that's this, is equal to x2. We just put a 1 in the column that multiplies x2. To write down x2 dot, so that's this term, equal to this equation. That means we have a minus a0 where we multiply x1 and a minus a1 where we multiply x2. And so this is our A matrix. And so now we're interested in computing the eigenvalues of this A matrix. And so the eigenvalues are where the determinant, the values of lambda, where A minus lambda I, its determinant is 0. And so A is given by this matrix. So A minus lambda I, we subtract lambda on the diagonal. So we get minus lambda from the minus I part. That's from A. We get this from A, and we get this from A minus the lambda I term. So when we take the determinant, that's this product minus this product. And so that would be minus lambda times minus A1 minus lambda, and then minus a negative A0. And when you simplify that, that becomes this expression. And it is no coincidence that this expression, even though this is in terms of lambdas, and the previous activity had this in terms of s's, and the previous part of that activity had it in terms of r, these are all the same fundamental characteristic equation that specifies the important behavior about this particular system. So it doesn't matter if we approach it with a mathematic perspective, with a Laplace transform perspective, or the state space perspective, we get the same equation characterizing the solution. And so we're going to go ahead, because it's the same quadratic form, to say that the two eigenvalues are R1 and R2, because that's effectively the solutions we would get. And based on our solutions from linear vector valued systems, we know that we would get something that looks like this, or we can also write that in terms of some coefficient times this exponential term in terms of the eigenvalue and its corresponding eigenvector, and the eigenvalue of the second eigenvalue and the eigenvector that corresponds to it. So again, we would get a very similar term, and in this case, this would end up simplifying. Once we calculated y of t, this would simplify down to exactly what we got before. Notice what we're calculating here is x of t, and so it makes sense that it would be vector valued, so it has two terms in it. Once we solve this down and multiply this out, y of t, right, x of t contains y and y dot, so y and y dot. So this would end up, y of t would simply just be the first row out of this solution, x of t.